Welcome to all learners. Today we begin a completely new way of learning digital logic design, where you'll use artificial intelligence to understand and work with hardware description languages like Verilog and VHDL. Traditionally, learning HDL was considered a technical challenge, especially for students without a coding background. But the goal of this course is to simplify that traditional approach. Instead of memorizing syntax or struggling with installations, we will show you how to use AI tools like ChatGPT and Gemini to build HDL projects. Using Google Colab, a free cloud platform, you'll be able to simulate, debug, and document your designs. This session lays the foundation for the rest of the course. By the end of this journey, you won't just understand HDL, you'll be confident in designing and simulating real-world circuits with AI as your co-pilot. Usually when we talk about learning Verilog or VHDL, we imagine a long list of syntax rules, complicated tools, and installation problems. But this course does not follow that traditional path. Here, the learning is fully AI-guided. You will describe each concept in plain English, and AI tools will convert it into Verilog or VHDL code. From design to debugging to simulation, every step will be assisted by AI. In traditional methods, a lot of time is spent fixing syntax and resolving errors. Here, you can focus on the logic and understanding. Best of all, there's no need to install heavy software, just a browser is enough. That's what makes this course useful, not only for non-coders, but also for working professionals and educators. The key benefit of this approach is that you will gradually adopt a learning method that is scalable, repeatable, and AI-assisted, making your learning journey efficient and truly hands-on. Most students struggle with digital logic design, not because the concepts are too difficult, but because the tools and syntax make the process frustrating. Verilog and VHDL have a steep learning curve. Installation of local EDA tools can be time-consuming and confusing. Even writing a test bench feels like a chore. There's no instant feedback, and when things go wrong, you have to debug alone. This slide introduces the pain points that almost every learner experiences. By understanding these struggles, we can better appreciate the power of an AI-assisted learning model, where syntax and tool issues no longer block progress. Traditional learning workflows rely heavily on complex desktop environments, license-restricted simulators, and manual scripting. Syntax must be perfect, file structures must be correct, and the simulation process is rarely intuitive. Students are often left to figure out test benches, waveform generation, and debugging on their own. There's no smart assistant to guide them. This slide shows how traditional methods put unnecessary pressure on the learner, turning what could be an enjoyable design activity into a stressful coding task. Our solution avoids these traps by using AI and cloud tools. Now, everything is changing. AI tools like Gemini and ChatGPT are revolutionizing how we approach digital design. You can simply describe a logic circuit in plain English, and the AI will generate synthesizable Verilog or VHDL code for you. Even test benches and debug routines can be auto-generated. Instead of getting stuck with syntax errors, you now get real-time help, explanations, and working modules instantly. This lets you learn by doing, which is far more effective than memorizing syntax. This slide marks the turning point from traditional to AI-augmented learning. So what makes our approach better? It's browser-based, cloud-powered, and fully AI-integrated. You don't need to install anything. All your simulation work will happen in Google Colab. You simply provide prompts. The AI handles the code. You'll use open-source tools like Icarus Verilog and GTKWave and view your results just like a pro. This approach works not only for beginners, but also for educators, freelancers, and working engineers. We remove the biggest barriers, coding and setup, so that you can focus on what matters, learning and logic design. Now let's see AI in action. In this demo, we'll use Gemini along with Google Colab to design, simulate, and verify a simple Verilog circuit, all without writing code manually. You'll see how AI handles HDL generation, test bench creation, simulation steps, and waveform analysis. This is especially useful for beginners and non-coders. Everything runs directly in the browser, and we'll use only open-source tools. Let's begin by setting up the environment. Now let's see AI in action. Let's now walk through the exact steps to begin your AI-assisted Verilog design demo using Google Colab and Gemini. First, open your browser and go to google.com. In the search bar, type Google Colab and click on the official Colab website. Once you're there, create a new notebook by going to File and selecting New Notebook. A new notebook will open in a separate tab. At the top left, click on the title and change the name to something meaningful. Next, open the PDF that contains your Gemini prompts. Copy the prompt for the first step, like installing tools or writing Verilog. Then go back to your Colab notebook. On the right-hand side, look for the Gemini Assistant panel. Click on it to activate it. Paste your prompt and hit Enter. Gemini will now generate Colab cells, some with code, others with markdown explanations. Review them, insert the suggested cells into your notebook, and you're ready to run your AI-powered HDL workflow. Our first step is tool installation. Since Colab runs on Ubuntu, we can install Icarus Verilog using a simple bash command. We'll use the apt-get package manager to install iVerilog and VVP, the two tools needed for Verilog compilation and simulation. After installation, we'll run version commands to confirm that everything is set up correctly. This setup happens in seconds. No downloads or drivers needed on your system. Now that tools are ready, let's generate Verilog code using Gemini. We'll start with a basic 2:1 multiplexer, one of the simplest and most essential combinational logic circuits. You just tell Gemini what you want: MUX with inputs A, B, and cell and output Y. Gemini will generate clean, synthesizable Verilog code using dataflow modeling and save it directly in your Colab workspace using %write file. With the Verilog module in place, the next step is testing. We need to create a test bench that simulates all possible combinations of A, B, and A cell. Gemini helps us here too. It generates a test bench that applies inputs, instantiates the module, and includes $display, statements and a waveform dump using $dump file and $dump vars. This lets us observe output behavior over time. Now let's compile and simulate the design. We use iVerilog to compile both the module and the test bench into a single simulation output file. Then we run the simulation using VVP, which executes the test bench. During simulation, the waveform data is written into a file called mux2to1.vcd, which we'll use for signal analysis. At the end, we list files to ensure the .vcd file was created successfully. With simulation done, we now download the .vcd waveform file from Colab to our local machine. This file contains the timing and logic level transitions for all signals during simulation. We'll also demonstrate how to optionally zip all related files, HDL source, logs, outputs, and download them as a single archive. These steps make it easy to store, share, or analyze your design offline. Now that we've downloaded the waveform file, let's learn how to open and view it using GTKWave. First, use the download link provided in the video description to get GTKWave for your operating system. Once downloaded, save it in a folder and extract the zip file. Open the extracted folder, go to the bin directory, and double-click on gtkwave.exe to launch the waveform viewer. Once GTKWave opens, click on File right pointing arrow, open New tab. A dialog box will appear. Here, select the .vcd file that you downloaded from Colab. GTKWave will now open a new window with signal groups on the left. From the module list, select MUX221 or your top-level module. Hold the Shift key to select multiple signals like MUX Sinde, B, Cell and VLSI. Then click the Append button to add them to the waveform viewer. You will now see the full waveform. Verify the output. When the select line, cell is low, the output Y follows input A, and when cell is high, the output follows input B. This confirms that the MUX logic is working correctly, and that your design generated entirely using AI is functionally valid. Congratulations! You've just completed a full digital logic design workflow using AI and open source tools, all inside your browser. You saw how easy it is to generate Verilog code using Gemini, create test benches, simulate your designs in Google Colab using Icarus Verilog, and analyze the waveform using GTKWave. The best part? You didn't write a single line of code manually. You used plain English prompts and let the AI do the heavy lifting. This not only makes learning more accessible, but also saves you hours of time. Now, what's next? Try extending this demo with more complex circuits like 4:1 multiplexers, full adders, flip-flops, or counters. You can follow the same prompt-based structure to build and simulate any digital circuit you want. Keep exploring, keep experimenting, and remember, with AI and Colab, learning HDL has never been this simple, scalable, and hands-on. Thank you for watching this demo on AI-assisted digital logic design. If you found this video helpful, please give it a thumbs up and consider subscribing to our YouTube channel for more tutorials like this. We regularly post hands-on content on AI, Verilog, simulation tools, and more. Also, if you're serious about mastering this approach, check out our complete Udemy course, AI-Augmented Digital Logic Design, from Elementary to Master. This course isn't just about digital logic design, it's about how to use AI effectively to learn, simulate, debug, and document HDL-based designs. It's ideal for students, educators, and professionals who want a modern, scalable way to learn HDL. The course link is provided in the description below. Your support helps us build more resources for learners like you. See you in the next video.